everyone. Welcome back to Learning at 11th Hour. So, in the last video, we talked about the branch current method and the mesh current method. And we had said that we are going to see how we can extend the mesh current method to apply to larger circuits with more number of loops. So, here we can identify the number of loops to be three, as we can see visually. Even using the empirical formula, we can find out that the number of individual loops L is going to be 3, because here we have 7 branches and we have 5 nodes. So since B is 7 and N is 5 and L is actually given by B minus N plus 1, so we get L to be equal to 3. So here we have the 3 loops or the 3 meshes, closed paths. So we have 3 circulating currents marked here as I1, I2 and I3. Now we are going to apply KVL at each of these loops. So for that, first let's mark the voltage drop directions. So here this would be positive, negative, and from in resistor RB there are two currents flowing. The first one is I1, the second one is I2. So the drop due to I1 would be in this direction from positive to negative, but the drop due to I2, see, I2 is entering RB over here, so I'll mark this as positive and this terminal as negative. So the drop would be in the upward direction. And for RA, it is quite simple. The drop will be in this direction. The assumed direction here is the direction of the circulating current. The drop VA would be in this direction. So when we write the KVL at loop 1, so I can write it as minus VA plus I1 RA plus I1 RB minus I2 RB, because we are looking at loop 1. So we consider that the direction of I1 is positive. Therefore, the direction of I2, which is opposing the direction of I1, is going to be negative, which is why the minus sign for I2. So now this is going to be all put together and be equal to 0. So we can rewrite this equation as I1 RA plus RB minus I2 RB is equal to VA. So this is my first equation. Let us now look at KVL at loop 2. So if we apply KVL at loop 2, so we need to mark the voltage drops. Look at I2 current. So it's entering here, leaving here, entering RD here, leaving here, and I3 is entering here and leaving here. Now we can mark the voltage drop directions pointing from positive to negative, here positive to negative. So now we can write the equation as I2 into RB, this voltage drop, plus I2 into RB, considering that the direction of I2 is positive. So plus I2 RB minus I1 into RB. Then let's look at RC, plus I2 into RC. Now looking at RD, plus I2 RD minus I3 RD. There are no voltage sources in this loop, so therefore is equal to 0. So when we rewrite this equation, let's maintain the order of I1, I2 and I3 for the sake of simplicity. So we get minus I1 RB plus I2 RB plus RC plus RD minus I3 RD is equal to 0. So this becomes my second KVL equation for loop 2. So when I apply KVL at loop 3, what do I get? So again, let me mark the directions of the voltages as plus, minus, and this is already marked. So this would be my drop in this manner. So see here, we get I3 RD, considering the direction of I3 to be positive because we are looking at loop 3. So minus I2 RD, because the direction of I2 opposes the direction of I3. Then we'll have plus I3 RE plus VB is equal to 0. So if I keep I2 in the first, I2RD minus I2RD plus I3RD plus RE is equal to minus VB. So this becomes my third KVL equation. So now what I am going to do is I'm going to just take the coefficients of I1, I2 and I3 from the three equations and put it into one matrix. We are now going to frame a matrix equation looks like this. Matrix R into matrix I is matrix V. So let's try to frame the matrix equation in this manner. So for R, the coefficient matrix would be in this manner. The coefficient of I1 would be written first. So that is RA plus RB from the first equation. And coefficient of I2 is minus RB. There is no coefficient for I3, so I'll put it as 0. For the second equation, it is minus RB plus RC plus RD being the coefficient of I2 and minus RD being the coefficient of I3. For the third equation, there is no coefficients of I1, so I'll put that as 0. Then I have minus RD and RD plus RE as the coefficient of I3. So this is my R matrix. The I matrix would be a column matrix made up of all the loop currents I1, I2 and I3. And the voltage matrix is again a column matrix that is made up of these constants of these equations. So after we frame the matrix equation and we find the resistance matrix, the current matrix and the voltage matrix, we can solve this resistance matrix and we can compute the values of I1, I2 and I3. So this can be done by computing the determinant of R and applying the Cramer's rule or the matrix method. So we know we can find out I1 as del 1 by del, I2 as del 2 by del, and I3 as del 3 by del. Here, del is nothing but the determinant of the matrix R. Now, what is del 1, del 2, and del 3? So, if I want to compute del 1, I have to replace the first column with the constant uh, of these equations. So I can replace VA0 and minus VB in place of the first column of my resistance matrix and retain the rest of it. And minus RD, I can have a 0 here, RD and RD plus RE. Now, if I compute the determinant of this matrix, that would actually result in delta 1. So, if I want to compute delta 2, I have to replace my second column in the resistance matrix with the constants of my equation. And for delta 3, similarly, the third column has to be replaced with the constants, and after which I can compute its determinant to obtain that. So then I can perform delta 1 by delta to obtain I1, delta 2 by delta for I2, and delta 3 by delta for I3. So this is called the Cramer's method. On the other hand, we can simply also solve this problem by computing I1, I2, and I3 in the form of simultaneous equations. Let us now look at an example problem wherein we can apply the concept of N-mesh network and find out the different loop currents. So here the question says that we need to find out the current through the 12 ohm resistor. So to begin with, we can see that there are three loops over here and the loop currents have already been marked by me as I1, I2 and I3. So, according to the loop currents marked, the current through the 12 ohm resistor, that is I 12 ohm, is actually I3. So, essentially, we need to compute the value of I3 from mesh analysis. So let's begin with the first loop, this being loop 1, loop 2, and loop 3. So when we apply KVL at loop 1, what do we get? So this is my first loop current. So these would be my drop directions. So I can obtain the equation as minus 480 plus 4I1 plus 7I1 minus 7I2 is equal to 0. So I can say 11I1 minus 7I2 is equal to 480. This is my first equation. Now if I apply KVL at loop 2. So this is my second loop. Here this is the direction of my current. So this being plus, minus, and the other directions are already marked. So I can write the equation as 4. Okay, we have to also consider I3 while looking at the 4 ohms. So here we need to put a plus and a minus. So now this would be 4 I2 minus 4 I3. Then looking at the 600 volts, it is the drop is in the same direction as the loop current. So I'll keep it as plus 600 plus 7I2 minus 7I1, because now we are looking at loop 2. So we'll consider the direction of I2 to be positive, and I1 is therefore negative. All this put together is going to be 0. So now when I simplify this, I'm going to get minus 7I1 plus 7 plus 4 is 11I2 minus 4I3 is equal to minus 600. This is my second equation. Now if I have to apply KVL at loop 3. So this is my loop 3. I can write it as 12I3 plus 4 I3 minus I2 plus this 4 ohm resistor. So again plus 4 I3 minus I1 is equal to 0. So now when I simplify this, I will get 20 I3, 4 minus 4 I2 and minus 4 I1. So I'm trying to maintain the order of I1, I2 and I3 over here. So I'll get minus 4I1 minus 4I2 plus 20I3 is equal to 0. So this becomes my third equation. So now if I try to form the coefficient matrix, let me do that over here. So I can write 11 minus 7, 0. From equation 2, I can write the coefficients as minus 7, 11 and minus 4, and the coefficients of equation 3, minus 4, minus 4 and 20. So this is going to be my R matrix. So if I need to find out the value of I3, I should actually compute delta 3 by delta. In order to obtain the value of delta 3, I'll have to replace the third column with the constants of my equation. So how can I do that? So we can now write the matrix equation as this. So this is my R matrix as we already saw. Then we have the 3 loop currents which are unknown, and the constants is equal to V1. V1 was uh, plus 480. This is minus 600 and this is 0. So from the equations, we can write the constants like this. So if I want to find out I3, I need to compute del 3 by del. In order to find out del, I can find the determinant of this R matrix. In order to find out del 3, I'll have to replace the third column with this column matrix. So I can write it as 11, minus 7, 480, minus 7, 11, minus 4, minus 4, minus 4, and 20. So now I can find the determinant of this matrix, which is what del 3 would be. Once I get the value of both del and del 3, I can easily compute I3 as 4320 by 864, which comes out to be 5 amps. So therefore, the current through the 12 ohm resistor is actually nothing but 5 amps. So using the N-mesh network method, we can actually compute the different loop currents. We can alternatively use simultaneous equations also to find out the value of I1, I2, and I3. So that's all with today's video. In the next video, I'll meet you with a problem on loop current method with a dependent source. I hope this video was helpful to you. Please do subscribe to my channel. Thanks for watching.